Okay, we're going to look at how exponential notation is used in estimating quantities. Now that we know about positive and negative powers of 10, we can compare numbers and estimate how many times greater one quantity is compared to another. With our knowledge of laws of integer exponents, we can also do other computations to estimate quantities. So for our first example, this will be in your math journal, and again, you don't have to write down the problems word for word, but just kind of summarize the important information so that you're not spending so much time writing down kind of trivial type information. You want to make sure you write the steps for each example out, but keep the word problems down to a minimum. Alright, so here's our first word problem, or story problem. In 1723, the population of New York City was about 7,248. By 1870, almost 150 years later, the population had grown to 942,292. We want to determine approximately how many times greater the population was in 1870 compared to 1723. So, the word about in the question lets us know that we do not need to find a precise answer, so we will approximate both populations as powers of 10. Now that we know about positive and negative powers of 10, we can compare numbers and estimate how many times greater one quantity is compared to another. With our knowledge of the laws of integer exponents, we can also do other computations to estimate quantities. So, the population in 1723 is 7,248. Again, from our previous lesson, there is a number with the same number of nines that is going to be greater than or exceeds our number. And then we also have a power of 10, which will exceed that also. So in this case, 10,000 is greater than 7,248. And we can simplify that to 10 to the fourth power. Well, the same thing with the population in 1870. There is a number with a number of nines in it, or 9 digits. And there's also a number to the power of 10, which exceeds our 942,000 numbers. So we're going to be using 10 to the fourth power as our estimate and 10 to the sixth power as our estimate. So we want to compare the population in 1870 to the population in 1723. And since reasonably thinking about this, we know that the population has expanded or has gotten greater. We're going to be comparing 1870 to 1723. So that means we're going to put 10 to the sixth power, our estimate, over 10 to the fourth power. So we're comparing 1870 to 1723. Now we can use what we know about the laws of exponents to simplify the expression and answer the question. And that is, when we simplify, we get 10 to the second power. Because using our laws of exponents, we can subtract the exponents. So 6 minus 4 is 2. So therefore, there are about 100 times more people in New York City in 1870 compared to 1723. Because obviously 10 squared is 100. Alright, so with that information, go ahead and try exercise 1 on your own on the lesson worksheet, and then when you're done, go ahead and continue the video and check your answer. Alright, so this is what you should have, talking about the Federal Reserve. The household debt, again using the same steps as we did in the example. 7,122 is less than 9,999, which is less than 10,000. And then you have the U.S. debt, so you would have the comparison, 10 to the 14th power over 10 to the 4th power. And we would do the intermediate step of showing 14 minus 4 is 10. So therefore, the national debt is 10 to the 10th times power greater than the average household credit debt. Okay, for this discussion, or to continue this discussion, go ahead and write the examples and important key points, or summarize the ideas in your math journal. Alright, so continuing with our last example, if our calculations were more precise in the last example, we would have seen that the population of New York City actually increased by about 130 times from what it was in 1723 instead of 100 times, which is what we came up with. So in order to be more precise, we need to use estimations of our original numbers that are more precise than just powers of 10. So for example, we're going to stick with our New York City population. Instead of estimating the population of New York City at 7,248 to be 10 to the 4th power, which was 10,000, we can use a more precise estimation of 7 times 10 to the 3rd power, or 7,000. So using a single-digit integer times a power of 10 is more precise because we are rounding the population to the nearest thousand. Conversely, using only a power of 10, we are rounding the population to the nearest 10,000. So consider that the actual population is 7,248 and 10 to the 4th power is 10,000. Then to write this, rounding it to the nearest thousand, it would be 7 times 10 to the 3rd power, which is 7 times 1,000, which is 7,000. So which of these two estimations is closer to the actual population? Well, clearly the 7 times 10 to the 3rd power is the more precise estimation. Alright, so for example 2, let's compare the population of New York City to the population of New York State. Specifically, let's find out how many times greater the population of New York State is compared to that of New York City. So the population of New York City is 8,336,697. Let's round this number to the nearest million. This gives us 8 million. So written as a single-digit integer times the power of 10, we would have 8 million is equal to 8 times a million, or 8 times 6 to the, or 10 to the 6th power. So the population of New York State is 19,570,261. Rounding to the nearest million gives us 20 million, and written as a single-digit integer times the power of 10. Now remember, just because we say 20 million, that is not a single digit. So it's going to be 20 million is 2 times 10 to the 7th power, or 2 times 10 million. So to estimate the difference in size, we compare the state population to the city population. So again, the state population being bigger is going to be on top, or a numerator of our ratio. So this would be 2 times 10 to the 7th power over 8 times 10 to the 6th power. Now we simplify the expression to find the answer. So 2 times 10 to the 7th power over 8 times 10 to the 6th power. Using our product formula, we can split that up into 2 over 8 times 10 to the 7th over 10 to the 6th. And using our equivalent fractions and the first law of exponents, 2/8 is the same as 1/4. And 10 to the 7th over 10 to the 6th, when we subtract 7 minus 6, that leaves us with 1. So that would be 10 to the 1st power. So now converting our fraction 1/4 to a decimal, that would be 25 hundredths times 10, which leaves us with 2 5/10. So therefore, the population of the state is 2 5/10 times that of the city. All right, example 3. So there are about 9 billion devices connected to the internet. If a wireless router can support 300 devices, how many wireless routers are necessary to connect all 9 billion devices wirelessly? Again, please do not waste a lot of time copying this down word for word. Just write down the important information. So because 9 billion is a very large number, we should express it as a single-digit integer times a power of 10. So that would be 9 billion is 9 times 10 to the 9th power. The laws of exponents tells us that our calculations will be easier if we also express 300 as a single digit times a power of 10, even though 300 is much smaller. So we're going to represent 300 as 3 times 10 to the 2nd power. So we want to know how many wireless routers are necessary to support 9 billion devices, so we must divide. We're going to take the bigger number, 9 billion, and compare that to 300. So it'd be 9 times 10 to the 9th power over 3 times 10 to the 2nd power. So now we can simplify the expression to find the answer. And again, by using the product formula, we're going to separate the 9 and the 3 to make 9/3, and the 10 to the 9th power over 10 to the 2nd power. And then again, by using equivalent fractions in the first law of exponents, we get 3 times 10 to the 7th power, which is 30 million. So about 30 million routers are necessary to connect all the devices wirelessly. All right, it is your turn. You have exercises 2 through 4 on your lesson worksheet. Go ahead and try those and refer back to the examples if you need some guidance, and then check your answers when you are done. All right, so here is the answer to exercise 2. Go ahead and compare your answer to the answer here. If you have any questions, make sure you write it down and bring them to class. Once you're done with exercise 2, continue to exercise 3 and 4. All right, and here are the answers for exercise 3 and exercise 4. Once you're done checking your work, then go ahead and continue the video. All right, let's take a look at a couple of more examples. So again, in your math journal, the average American household spends about $40,000 each year. If there are about 1 times 10 to the 8th power households, what is the total amount of money spent by American households in 1 year? So we're going to express 40,000 as a single-digit integer times a power of 10. So that would be 4 times 10 to the 4th power. The question asks us how much money all American households spend in 1 year, which means that we're going to need to multiply the amount spent by one household by the total number of households. So instead of a division problem, which we have been working on, this one is actually going to be a multiplication problem. So now we have the product of 4 times 10 to the 4th power times the product of 1 times 10 to the 8th power. And again, by repeated use of associative and commutative properties, we basically have 4 times, and we can move these around, 4 times 1, so we're going to put those two factors together, and then 10 to the 4th power times 10 to the 8th power. Because again, commutative and associative properties of multiplication, you are allowed to do this. So that means simplifying, 4 times 1 is 4, and because of the first law of exponents, when I have bases that are the same, I can add the exponents, so 4 plus 8 is 12, and that is how we get 10 to the 12th power. So therefore, American households spend about, and get this, $4 trillion each year altogether. All right, exercise 5. Go ahead and complete exercise 5 on your lesson worksheet, and when you're done, continue the video to check your answer. All right, so here is exercise 5. If you have any questions about the answer or how it was gotten to, then go ahead and write down your question and bring it to class. All right, so let's wrap this up. In general, close approximation of quantities will lead to more precise answers. We can multiply and divide numbers that are written in the form of a single-digit integer times a power of 10. All right, we'll see you in class.